We have already discussed about the rotational spectrum and vibrational spectrum of a diatomic molecule. So rotational spectrum arises due to the transition between rotational energy levels, which are rotational energy levels, where rotational energy is small in magnitude, which appears in microwave region. And vibrational spectrum is because of the transition between vibrational energy levels, which appears in infrared region. And we have seen that the rotational spectrum of a diatomic molecule is having equally spaced lines, where separation between these rotational spectral lines is equal to 2b centimeter inverse, where b is the rotational constant. Where vibrational spectrum is having a single line if you consider the diatomic molecule as a simple harmonic oscillator. So these two concepts you have covered in the previous class. So let us take the combination of this rotation and vibrational spectrum. Suppose the vibration and rotation of the molecule are considered together, then this gives rise to a spectrum called RV spectrum, or rotational vibrational spectrum. We call it as RV spectrum. So we consider the vibrations and rotations of a molecule takes place independent of each other. Okay, so vibration is independent of rotation and rotation is independent of vibration. And you can add the total energy. You can get the total energy by adding the rotational energy and vibrational energy in a simple addition. So that is the meaning of the independent nature of vibration and rotation motion of the molecule. The molecule can be considered as vibrating rotator, which gives combined rotation and vibrational energy of the molecule. So we consider a molecule as a vibrating rotator. It is vibrating as well as rotating because of its continuous motion. So vibration gives rise to certain energy, and rotation of the molecule also gives rise to the rotational energy for the molecule. Then under these circumstances, the total energy of the diatomic molecule, by considering the vibration and rotational motion, which can be expressed in wave number units, and that is given by the sum of vibrational energy and rotational energy. So total energy EV, J is equal to EV plus EJ in centimeter inverse, where EV is the vibrational energy, V stands for the vibrational quantum number, EJ is the rotational energy, where J stands for the rotational quantum number. Okay, so EV, J represents total energy of a vibrating rotator. So what is the value of vibrational energy in centimeter inverse? And what is the energy of rotating molecule in centimeter inverse? Already we have discussed. Therefore, total energy EVJ is equal to V plus half into nu bar, where nu bar is the wave number of the spectral line. V is the vibrational quantum number. Similarly, the rotational energy plus B into J plus 1 is obtained, where B is called as rotational constant, that is having the value h divided by 8 pi square I into C, where J is the rotational quantum number. So this is in terms of the wave number unit, that is in centimeter inverse. Here V is the vibrational quantum number, nu bar is the wave number of vibrational spectral line, B is equal to h by 8 pi square into IC, which is called as rotational constant of a molecule, and J is the rotational quantum number. So these two expressions are obtained in the previous classes, vibrational energy and rotational energy. Just you have added them to get the total energy of the vibrating rotator. Here EV is very much larger than EJ. If you calculate properly, the vibrational energy is very much larger than the rotational energy. And you can find number of rotational energy level for a given vibrational energy level. That means for a given vibrational energy level, you can have number of rotational energy levels in that. Okay. There are vibrational energy levels ಒಳಗಡೆ ಮತ್ತೆ number of rotational energy levels ಇರ್ತವೆ. So that we will try to represent pictorially. So the allowed transitions are represented by selection rules. So as in vibrational spectra and rotational spectra, here same selection rules are going to be allowed. That is, delta V should be equal to plus or minus 1 and delta J should be equal to plus or minus 1. So V can change by 1 and J can change by 1. Okay, so these are representing the allowed transition and they are called as selection rules. Let us consider a transition of the molecule from V equal to 0 state to V equal to 1 vibrational level by the absorption of energy. So molecule absorbs the energy in infrared region. So infrared photon is absorbed by the molecule and it can go from V equal to 0 level to V equal to 1 level. So vibrational energy level is going to change. Then vibrational levels contain number of rotational energy levels. Okay, so V equal to 0 contains J equal to 0, 1, 2, 3, etc. Similarly, V equal to 1 vibrational level contains again J equal to 0, 1, 2, 3, etc. Let us take J dash and J double dash be the rotational quantum numbers in V equal to 1 state and V equal to 0 state respectively. That is, J dash is in V equal to 1 state, J double dash represents V equal to 0 state. So J dash is higher state, J double dash represents the lower state. The allowed transition and rotation vibration spectra of the diatomic molecule can be represented in a next slide. We'll represent that in a next slide. Okay, so we'll show the energy levels and also I will show the allowed transitions and how does the rotational vibration spectra looks like. So this figure represents or this shows the different energy levels and allowed transitions. So these energy levels corresponds to V equal to 0 state and here V equal to 1 state is there. In V equal to 0 state, you can observe number of rotational energy levels and you know that the rotational energy levels are not equally spaced. They are having the increasing separation. J double dash represents the rotational quantum number in lower vibrational state. J dash represents the rotational quantum number in higher vibrational state. Okay, so here 0, 1, 2, 3, 4, 5, 6 rotational energy levels are considered in V equal to 0 state and 6 rotational energy levels are considered in upper vibrational state. Remember, vibrational states contains number of rotational states. Okay, so this concept you have to understand properly. So here, what are the allowed transition? Remember, the selection rule for V is delta V equal to plus or minus 1. So molecule can go from V equal to 0 to V equal to 1 state. It can go from lower state to upper state, but it has to satisfy delta J equal to plus or minus 1 selection rule also. So it cannot go from any level to any level. It can go from some J value, the molecule in J equal to 0 state can go to J equal to 1 state. So J must change by only 1, plus 1 or minus 1. Similarly, the molecule in J equal to 1 state can go to J equal to 0 or it can go to J equal to 2. Okay, so two possibilities are there. The transitions corresponding to delta J equal to plus 1 and there are some transition corresponding to delta J equal to minus 1. Okay, let us take the case of delta J equal to plus 1. Let us take the first allowed transition. Let us take a molecule in J equal to 0 state. It can go to J equal to 1. So initial value of J is 0. Final value of J is 1. So final minus initial is plus 1. So this is allowed transition where J is changing by only 1. Where J equal to 0 to 2 is not possible because J is going to change by 2. That is not allowed. Now consider a molecule in J equal to 1 state here. It can go to J equal to 2. Here also the value of J is increased by 1. It is going from j equal to 1 to j equal to 2. J is increased by 1, so delta J is plus 1. Similarly, molecule can go from j equal to 2 to j equal to 3. Similarly, j equal to 3 to j equal to 4, it can make the transition. And these transition gives rise to certain lines, and they are represented by R0, R1, R2, etc., where this subscript represents the lower energy state J value. So here J equal to 0 to J equal to 1 gives rise to R0 line. And the condition of selection rule with delta J equal to plus 1 gives you R branch lines. So these lines are called as R branch lines, for which delta J equal to plus 1. Now consider the second case, delta J equal to minus 1 case. Let us take the molecule at J equal to 1 state, it can go to J equal to 0. So J is decreased by 1. It is going from J equal to 1 to 0. So delta J is minus 1. Okay. So this gives rise to one line called P1. Similarly, J equal to 2 to 1 is allowed, 3 to 2 is allowed, 4 to 3 is allowed, where J is decreasing by 1. So therefore delta J equal to minus 1. So energy difference is lesser here. That's why they appear in the lower wave number side. Here energy gap is more. That's why these lines appear in higher wave number side. Okay, so energy difference represents the energy of that line or frequency of that line. Okay, so delta J equal to minus 1 selection rule gives rise to P branch lines called P1, P2, P3, etc. Again, the subscript representing the lower J value, the lower energy state J value. Here it is going from 1 to 0. So P1 is obtained, P2, P3, P4, P5, P6 like that. The central line is observed for anharmonic oscillator, but for harmonic oscillator you will not get central line. And here the separation between R0 to P1 is equal to 4b. And next, the separation between the lines are equal to 2b. Okay, in pre-branch line also, the separation between the spectral lines is equal to 2b centimeter inverse. And in R branch lines also, the separation between the spectral lines is equal to 2b centimeter inverse, where the separation between R branch, the first line of the R branch and first line of the P branch is equal to 4b. And that is observed for the diatomic molecule. So this explains the energy levels, allowed transitions, and spectrum observed. You have already done an experiment on RV spectrum. You have done the experiment on HBr molecule, which is a diatomic molecule. And you can find P branch lines and R branch lines in a RV spectrum of the HBr molecule. And this is the concept behind that RV spectrum. Now you observe for the transition, delta J equal to minus 1, the spectral lines are called as P branch lines. And for delta J equal to plus 1, the spectral lines are called as R branch lines. Already I have explained you initial value of J to final value of J. You take the difference. If J is increasing, then delta J equal to plus 1. That they are called as R branch lines, and R branch lines are on higher wave number side and P branch lines are on lower wave number side because of the lesser energy gap between the energy levels here. The center of the spectrum has wave number nu bar, which is called as band center or band origin. So that is observed because of the vibrational energy level transition. That is V equal to 0 to V equal to 1 transition. And that is having a single line observed at the center, which is called as band center or band origin. Okay. The energy difference for the allowed transitions can be expressed in the form of the mathematical expression. Now, difference or change in energy because of the transition of the molecule is given by delta EVJ is equal to nu bar plus 2b into J plus 1. First term is because of the vibrational energy difference. Second term is because of the rotational energy difference. So total difference of energy is equal to nu bar plus 2b into j plus 1, so much of centimeter inverse. Now for the transition delta j equal to -1, the spectral lines are called as p branch lines, already have told you, and delta j equal to +1 gives you r branch lines. The center of the spectrum is a nu bar, and which is called as band center or band origin. And finally, the RV spectrum, in the RV spectrum, the spectral lines are separated by 2b centimeter inverse. If you find the separation between the spectral lines in the RV spectrum, you can find the value of B. Always the separation between the spectral line is equal to 2b. So B can be found. If you know the value of B, you can find out the moment of inertia by using the general expression. And if you know the moment of inertia, you can find the bond length of the molecule or the equilibrium distance between the atoms of the molecule. And P branch and R branch lines are separated by 4b centimeter inverse. The first line of the R branch and first line of the P branch are separated by the 4b centimeter inverse, the wave number unit. Okay, and that has to be remembered. You remember in RV spectrum, the spectral lines are separated by 2b centimeter inverse. If you know this separation between the lines, you can find the value of B, and hence you can find the moment of inertia and the internuclear distance. So that is about the RV spectrum.